Edexcel Core Pure First Order Differential Equation, applying the separation of variables method. In a previous video we looked at how we created the first order differential equation to represent Newton's law of cooling. It's very important here that we are aware of how the rate of change works. So for example, the initial rate at which it is cooling is 5 degrees Celsius per minute. So in order to lose, for example, 20 degrees Celsius, the answer is not 4 minutes. We can't say that the rate of change of the temperature with respect to time is -5. It's not a constant rate of change, so that does not give us a valid model for this problem. The valid model we need is that the rate of change of temperature with respect to time is minus K times T minus 20, where T minus 20 is the temperature of the object above the room temperature. So the answer isn't 4 minutes, and we have created our differential equation based on the temperature above the room temperature, and we know that the rate of change of temperature is both negative and proportional to T minus 20. Although this is a recap of some of the theory used in A-level mathematics, it is extremely important in the study of the further mathematics content. So here is our first order linear differential equation, and I'm going to go straight to separating the variables. So I'm going to leave the temperature where it is. I'm going to divide both sides by T minus 20. I'm going to leave the minus K where it is, and I'm going to times both sides by dt for time. You must at that stage, having separated the variables, put the integral signs in. So although normally we don't treat dt by dtime as two separate terms, the notation is flexible enough to deal with that when we multiply both sides by dt. It does give us a valid approach. So doing the integration on the left hand side is ln t minus 20, integrating the right hand side minus kt plus 1 constant of integration c. You do not need 1 on both sides. If we know what ln t minus 20 is, then t minus 20 is e to the minus kt plus c. And a couple of things we can do here. We can add 20 to both sides, but we can also write this as e to the c times e to the minus kt, which gives us a general solution of t is 20 plus, and I'm going to replace e to the c with a different constant. I'm going to call it capital A. So if I stop there, that would be my general solution. T equals 20 plus arbitrary constant A times e to the minus kt. K, remember, is a constant of proportionality, not a constant of integration. So to recap, I divided both sides by t minus 20 and I multiplied both sides by dt. Make sure you put the integral sign in. So we have an integral dt and an integral d capital T on one side. Once we have integrated, you need a single constant, and that single constant has been eventually written and replaced by capital A. That's where the constant of integration is, and this is our general solution. Now we need to look at some of the given information in order to find the constant of proportionality K and the constant of integration A. So what do we know? We know that initially, that means that times 0, we know that initially the rate of change of the temperature was 5 degrees per minute, and we know that it was losing temperature, so it must be minus 5 degrees per minute. So if we put this information, these conditions into the differential equation, we get minus 5 equals minus k 80 minus 20, therefore k is 1/12. So now we can put the value of k into our general solution, so that's where we're at now, and we need to use the conditions that initially, so that's time is 0, the temperature of the object was 80. That will give us 80 equals 20 plus a e to the 0. So that's 60 equals a, and e to the 0 is 1. So we now know that a is 60, t is 20 plus 60 e to the minus a 12th of t. So it's important to distinguish how we found the constant of proportionality k. So we use that based on the initial rate of change of temperature, which is not constant. That is just the rate of change when t is 0. So now we can look at how long it will take for this coffee to cool by 20 degrees Celsius. We know that the answer isn't going to be 4 minutes. It's not losing 5 degrees Celsius every minute. So we need to be able to find the correct time using this particular solution. So we know that when t is 60 degrees Celsius, and we want to know the time t when that happens. So 60 degrees Celsius for the temperature of the object equals 20 plus 60 e to the minus a 12th of t, and take away 20 and divide by this 60 will give us 2/3 is e to the minus a 12th of t, and therefore if we use natural logarithms, the natural logarithm of 2/3 must be minus a 12th of t. Sometimes students look at that and think they're going to get a negative answer for t, but of course ln of 2/3 will also be negative, so we've got a negative equals a negative, and if we do this on a calculator we get the time equals 4.87 minutes to 2 decimal places. So if the temperature dropped by 20 degrees Celsius, that means the actual temperature of the object was 60 degrees Celsius, and that happened when the time was 4.87 minutes. So if we look at this particular solution as a graph, it satisfies the conditions that when t0 the temperature of the object was 80, and the gradient at that point, and only at that point, the gradient was -5. That was the rate of change of temperature at the beginning. But if we now look at when the temperature is 60 degrees Celsius, we can read off the time as 4.87 minutes. The other thing that's interesting here is if we look at the long-term effect, so let the time tend to infinity and get bigger and bigger, we can see that we're getting exponential decay and that the temperature of the object gets closer and closer to 20 degrees Celsius, which is the temperature of the room. So in the next video we're going to be looking at the integrating factor and multiplying by a factor to give a perfect derivative.